starting there. Yeah, I think we're online. So, hi everyone, welcome to our end of the year meetup. This is going to be the last session for our 2017 meetups, and I'm seeing some new faces and some familiar faces. So, welcome everyone. Your attendance is really appreciated. That's really the key to keep this event a good learning and getting to experience for everyone. So my name is Annotation. I'm a research data scientist at Axial Healthcare. I'm also a co-organizer of this event. And this is the end of the year, and I do have a special request. I just want to shout out quickly to our organizer group. We have Chad Yu, who's the lead in our organizer group, and Eric Stevens with us here today. Christine Lai, she's out of the country right now, and also we have Lucas Lucasiak. Yes, thank you. So yes, I've been really volunteering their time to set up the venue, to get the pizza and to line up speakers. So it's some work for them, and can everyone just give a round of applause to our organizers. Also, on that note, just want to thank our sponsors very quickly. We have Axial Healthcare for pizza and for meetup website subscription. And also, we would like to thank Nashville Technology Council for offering this space for us. It's a really nice space. So we have a cocktail party next door, so you guys feel free to grab a cocktail after the presentation. So without further ado, please let me introduce our speaker today, Dr. Colin Compas. Colin actually hasn't lived here since high school, right? Yeah, in Nashville, and then he did his he got a bachelor of engineering from Vanderbilt, so he really loves Nashville, and now he moved back to Nashville. So he got his Bachelor of Engineering from Vanderbilt in 2007. After that, he went on and received his PhD from Yale University in Biomedical Engineering. During his PhD, he focused on quantification of cardiac function in echocardiography. So I have no idea what that means, but it sounds really fancy. So his background is in medical image analysis, where he worked to develop automated methods for anomaly detection in clinical disease. So that makes a lot of sense and sounds really good. Colin then joined IBM Research and worked to bring cognitive solutions to radiologists and cardiologists. His work at IBM was incorporated into the first products launched through IBM Watson Health Imaging. Earlier this year, Colin joined NVIDIA as a senior solutions architect, focusing on deep learning solutions for healthcare. His work has resulted in over 25 journal and conference publications. Very impressive. Everyone, please welcome Colin Compas.
Thank you for the introduction. I'm excited to be here to talk about what I think is probably one of the hottest areas of healthcare research right now, and that's the application of deep learning and artificial intelligence across a variety of different areas of the healthcare space. And so to get things kicked off, I just want to make sure that we're all sort of speaking about the same thing when we talk about these terms. They often get used sort of interchangeably, but artificial intelligence is a very broad area of study that has been around for many years, going back to the 50s, and possibly some would claim even slightly earlier than that, when some of these original ideas about teaching a computer to do something advanced as human thought started to come about. And in the early days, the results were relatively simple applications, playing the game of tic-tac-toe or checkers, and leading to a variety of science fiction movies of all of us, being taken over by machines, the whole world being taken over by machines. And there was a lot of challenges in the early stages of artificial intelligence development that sort of led to that area of research to kind of fall out of fashion for quite some time. And then with the adoption of sort of traditional machine learning techniques, the field started to become much more prevalent and much more popular. And what sort of happened in that meantime is the researchers went from having to do a lot of hand coding of rules and decisions, so a lot of if statements in their computer code to get these algorithms to do anything, to actually start to train these networks to do a task based on a given input data. So instead of having to hard code a lot of rules about making decisions, so if you were trying to classify a certain type of image, whether there's a dog or a cat, instead of having to hard code rules, you could start to figure out what the features are that are characteristic of dogs and cats, and then teach the network how to distinguish those two. And so machine learning has been, proven very successful for many different applications at this point. In the healthcare space, there's a lot of different ways that technology is being applied. Healthcare has the benefit of a lot of the data is in structured or semi-structured form that's relatively straightforward to pass to things like SPM or boosted trees, things like that for doing different types of classification. But the challenge with that is that it still requires manual annotation to identify what the features of interest are. And so that's sort of the problem that deep learning has sought to solve, is to, instead of manually identifying what features are going to be discriminant for a certain task, actually teaching the network to learn what those features are through examples. So if you wanted to do an example of classifying a dog versus a cat, instead of having to manually identify what the important distinguishing features between dogs and cats are, and then figuring out how you would code that into an algorithm, you actually just show the network many labeled examples of dogs, many labeled examples of cats, and then the network actually learns a representation to distinguish these two objects of interest. And at a high level, that is, seems very exciting. When we start to see what this technology can do in practice, it's very easy to start to extrapolate and think that this is going to solve every problem that we can possibly present. And that's leading to an incredibly large amount of hype surrounding this field right now. And so Gartner is a research and analytics organization. They put out this hype curve around different technologies that they see becoming popular. And what happens with this type of technology is that there's typically a peak, and expectations get really high, and we start to think that this is going to solve everything that we want. And then there's usually this period of sort of disillusionment when we start to actually implement a lot of this technology, and we see that things don't necessarily work as well as we had hoped. And right now, we're sort of at the peak with deep learning. So the field is still relatively immature in terms of practical applications. It's still a very active area of research, but it's really exciting. The type of problems that are being solved right now are there's just across all different types of industries, and so that's leading to this excitement. It's going to happen. There's going to be this period relatively soon where some of these expectations are not being met. People start to feel disenchanted with some of this technology. But I'm going to talk today about some of the ways that this is already being brought into practice. So they estimate that it will be sort of 2 to 5 years before we start to see some of this technology really proliferate into the markets. And I'm going to show you that that's a longer timeline than I actually believe. We're starting to see some of this technology really infiltrate the clinical markets right now. But the challenge comes from some of the claims that get made either by authors of research papers or then by the media when they start to try to interpret some of the results that are coming out of the academic community. And so what this results in is a lot of headlines saying that computers are going to replace doctors, computers are better than radiologists, computers are better than pathologists, better job than humans across the board. You know, the robot doctors are going to replace everyone in healthcare. I thought this one was pretty funny just because they served me up an NVIDIA ad right next to this article as I was reading this. And actually, just to take a step back, I realized I didn't say anything about our company. So NVIDIA makes GPUs. These are graphic processing units. So this is the hardware that is actually underlying a lot of the development within deep learning. They were originally developed for doing image visualization, playing video games. Until maybe 4 or 5 years ago, that's pretty much the way that anybody knew NVIDIA was. They were hardcore computer gamers, and they were looking to, you know, really accelerate the games that they were playing. And it turns out that the same type of mathematics that's used for doing visualization and image reconstruction is actually the same as what you need for training these deep learning algorithms. And as people realize that, turns out an overlap between people that want to do computer science and people that play computer games, and they can leverage this same hardware that they already had in really new and exciting ways. But these headlines just keep coming. Even this was today, as I was getting ready to come here, this came into my inbox, another story about AI matching radiologists in terms of their tasks. As May mentioned, I used to work for IBM Research, and we started delivering some of the technology into IBM Watson. And this headline goes back to 2014. So people were starting to try to make some of these jumps into this new area. And when Josh spoke at this event a couple months ago, he showed a slide like this. And there's been sort of some blowback recently, especially related to Watson and some of the claims that are being made that may not quite be as accurate as one would be led to believe based on these publications and PR announcements. I think IBM was in an unfortunate situation of a really large company. They have a really large marketing team, and the marketing team just got a little bit ahead of where the research was. But I'll also talk a little bit about why that is happening and why some of these comparisons that even the researchers are making to say that they are as good as or better than doctors don't necessarily make sense in a lot of cases. And so it's sort of just grandiose to get attention, but in a lot of cases, it's not actually, there's not actually a lot of substance behind it. And so why are we at the peak of that hype curve? Why is all of this deep learning technology really coming to the forefront right now when some of these original methods were developed as far back as the 50s? So there's sort of three things that have come together recently to empower this AI revolution. And that's the availability of data. So in order to train these networks, as you mentioned, if you're going to train something by showing it examples, you need to have huge amounts of data. And so we're talking about, on the order of hundreds of thousands to millions of images, labeled images that can be used to train these types of networks. And, with the internet and things like that, that's now possible. It's relatively straightforward to get large-scale collections of images, especially of natural scene images that you see, on any website on the internet. The second is the compute power, and so this is where NVIDIA comes in. We've created this underlying architecture that has allowed these networks to run in a highly efficient manner. And so doing network training that would be basically intractable in a lot of cases can now be done in minutes to hours, where if you were trying to do this on a CPU, you'd be looking at weeks or months to do sort of the same type of job. And then the third is that there have actually been algorithmic advances. So there have been underlying theoretical improvements that actually help to ensure that these networks are going to perform the way that you expect, converge in reasonable amounts of time, things like that. So these three things coming together has really been what spurred this current interest in artificial intelligence, and specifically this sort of sub-area of deep learning. When we talk about this different learning model, what do we mean sort of in an example? If we were to try to write a classifier to detect a car versus a motorcycle, at a high level, that seems relatively straightforward. Any child can do it. You show them examples. You say, when they see a car, yes, that's a car. Now they start to call everything that goes by on the street a car. And then you say, well, no, actually, that one's a truck, that's a motorcycle. And they start to inherently learn what the representation of these different categories are. In traditional machine learning, if you wanted to do that, you would have to say, to come up with some type of heuristic yourself that would identify and distinguish these different categories. So, for example, a motorcycle most likely has 2 wheels, whereas a car most likely has 4 wheels. Well, okay, now if you have an image, how do you actually encode what 2 wheels versus 4 wheels look like? Well, first you have to come up with a representation of what does a wheel look like in an image? Well, okay, so a wheel is a circle. So now you have to come up with basically a circle detector. And so now if you know you have this circle detector, you could then feed that, the output of this circle detector into some other kind of classification network. And now you could say, okay, it will learn that things with 2 wheels are typically motorcycles, things with 4 wheels are typically cars. Okay, now what about a truck that may have more than 4 wheels? How do you do that? Well, now you have to keep adapting this approach. Or if now something doesn't quite meet that characteristic where you have some kind of hybrid motorcycle with 3 wheels, well, now you need to come up with another rule that says, okay, maybe if it has a roof, it's a car, and if it doesn't, it's a motorcycle. These types of problems can really start to escalate as the complexity of your data increases. And so the way that we're able to solve that with deep learning is that now these features are no longer hand-tuned. So by just showing the network examples of many, many cars, many, many motorcycles, the network actually starts to learn how to differentiate these different classes. And so this, you can see then, is really powerful as you start to scale out to many different examples. If now you wanted to add a third class, say trucks, you can just create more training data, update your network, and now you'll be able to handle this new unseen class of objects. What does this training process look like? So the first thing that you have to do is define your network architecture. This is going to be the structure of this deep neural network that you're going to use for a specific task. Different architectures are going to be more powerful for different types of tasks. So if you wanted to do classification, so giving a single label to an overall image, that might be one type of network architecture. If you wanted to do object detection, actually localizing individual images within that overall scene. So for example, if you had you were doing a self-driving car and you wanted to be able to identify where all the pedestrians are, that would be an example of object detection. The network architecture for something like that would be different. And so just sort of some of the common terms that you'll hear that people are going to use when they describe these networks. So each of these sets of green dots is going to be a layer in your network. The individual green points here are the nodes in the network, and they're all connected by a series of weights. And so in this particular example, this is just a 4-layer network. So we have an input layer on the top, we have 2 hidden layers in the middle, and then an output layer on the bottom. And so the output there would be the different classes in this particular instance. So if we wanted to, say, classify dogs and cats, the output layer would just be a probabilistic prediction of whether the input that we're seeing is a dog or a cat. And so now that you've defined this architecture, and typically when we're talking about deep learning, it would be many, many layers, not just 4 layers. And so as you increase the number of layers in your network, you increase the complexity that this network can learn. So it can learn to distinguish based on more and more complex features of the different classes that you're trying to represent. So when you define what the task is, you would create this label training set. You would then pass this through the network. These weights would be updated in an iterative process. And slowly this network learns what the important features are for distinguishing these 2 classes. And the way that it does that is at the beginning, each of these nodes has a weight associated with it. And you start typically with some random weights. And then each time the image is passed through, either it gets this correct or it gets this incorrect. And since these are labeled, you know what the expected output should be, and you can actually then identify which nodes in the graph were contributing to the correct or incorrect prediction, and then you can update those weights accordingly. So you can strengthen the connections that are leading to correct classification, and you can weaken the connections that are leading to an incorrect classification. And eventually, this will start to converge to some stable state, and then that is the overall network architecture that you would then have. So when you have this trained model, that's essentially what you have. You have this network with a set of associated weights. And what has been really powerful about this technology is that some of these networks both the architectures and the corresponding weights have proven to be very good at doing many different tasks. So just because it's trained in one domain, you can start to apply some of the same technology with sort of minimal updates in new areas. And that's what's allowed for really rapid progression within this. And in all of these frameworks, people are not writing all of this from scratch. They're leveraging a wealth of knowledge that's in these open source communities around these deep learning frameworks. So if you've heard of things like TensorFlow or Caffe or MXNet, those are some of the PyTorch, those are some of the popular deep learning frameworks that have built into them the ability to define these different types of architectures, ways to optimize the training of these networks, and then once you have that trained network, methods for deploying that technology so that you can actually use it. So when you actually want to use something like this, then the process is called inference. And so that's when you pass a new unseen object through that network and get some kind of result out. So in this particular case, whether it's a cat or a dog. And so now if we then said, okay, we've defined our network, we've trained it, it's performing very well on distinguishing cats versus dogs, but now I have a picture of a raccoon. So I pass that through the network, it's probably going to say, with about equal probability, it's either a cat or a dog. It doesn't really know very much about a raccoon. But if you wanted to then leverage that same network, you can simply add one more node to your output of your task. So now you have 3 classes, cat, dog, raccoon. Collect some more training examples and go through that training process again in an iterative fashion. You're just sort of updating some of the knowledge that you've already developed. So some of the same features that are going to be useful for characterizing cats versus dogs are also going to be relevant when you now try to classify a raccoon. So you can quickly adapt the network to specific new use cases without having to go back to the drawing board and sort of hand engineer all of these new features that you're interested in. And so this is all sort of very general. So where are we starting to see this type of technology being applied in the healthcare space? So I'll focus mostly on the imaging domain. That's my background. That's where I work with a lot. It's where these technologies are really starting to make their way into market the fastest. We'll give you a few examples outside of imaging, but the sort of 3 types of tasks that people would typically do with this type of architecture in the medical domain are classification. So whether an image is normal or abnormal, if you were trying to do bone age, which is a really common task that radiologists have to do, but it's also very tedious, and they have to look in an encyclopedia and match an image to a template. And so that's sort of a very natural thing for an algorithm like this to do, to learn this representation and assign a single label to that image. So that's classification. Object detection, as you mentioned in the self-driving car case, but in something like this, in a pathology image, you would be trying to identify specific abnormal cells, or if you were looking at an X-ray, the region where the fracture occurs in the image. Those would be object detection tasks. And then from the image segmentation standpoint, that's actually doing a pixel level classification. So identifying and giving a label to the individual regions within the image. And so in this case, it would be segmenting out, identifying the boundaries of a tumor in a brain MRI scan. And so there's a lot of value to being able to do that in a very accurate way. If you were trying to track the progression of disease or response to a treatment, being able to quantify the volume of a tumor is going to be really, really important. So how have we seen this technology transfer from sort of the general computer vision domain into the healthcare space? So ImageNet is one of the first places where this type of technology was really applied at scale and got a lot of attention. So what ImageNet is a challenge that's available in the, for general computer vision to do classification and object detection on natural scene images. So this is a collection of 1.2 million images with 1,000 object categories within. So this is a challenge that's been going on for quite a while now. It has a leaderboard that's posted every year. Different teams submit applications, and you can see how you're progressing, how the technology is progressing. So what we see here is that prior to 2012, all of the approaches were traditional computer vision approaches. So they were trying to distinguish all of these different classes. So people, cars, helmets, birds, frogs, and they were having to come up with representations of this type of data that could then be, use random forest or SVM or something like that to do classification. And you can see that, that's a pretty challenging task. How would you define, beyond simple features like edges and different contrast gradients and things like that, enough information to categorize 1,000 different things? And so we can see that for about 4 years, the progress using traditional computer vision approaches was relatively incremental. The best teams were maybe improving by 1 or 2% year over year. In 2012, the first teams submitted an application using deep learning. And you can see that the accuracy jump went up by over 10% in that first year. So if you're competing in a challenge year after year and seeing incremental gains of 1 or 2%, and then all of a sudden, 1 year, the results go up by 10%, that's going to get a lot of attention. So that's exactly what happened. You can see that the next year, there were still a few groups that hung on to the traditional computer vision-based features. They didn't do very well relative to these other approaches. And then by the following year, they were completely gone from the challenge. An entire community shifted from one way of thinking about these problems to a new way of thinking about problems in the span of just 2 years. And so that's incredibly rapid progress, but you can see why that was. The jump in accuracy was so large that there was no way to ignore the results that people were getting out of this, despite the fact that there are still many aspects of this technology that people don't quite understand at a theoretical level. It's a very experimental field at this point, but the results have been so powerful that there was no way to avoid it. And so now we're starting to see the same trend happen in the medical domain. So this is a review paper that came out earlier this year. And so we can see the types of technologies that people are doing for medical image analysis. And you can see that starting in 2015, the first instances of people using neural networks to do analytics start to show up. And then in 2016, there's a huge growth. And so we're seeing that across other conferences as well. So MICCAI and ISBI, those are two of the popular medical image analysis conferences, and we're seeing the same type of exponential growth in terms of usage of this technology. But what we're also seeing is that this technology is, we're looking at least 2 years behind when these techniques are being developed and deployed in sort of the general computer vision community. So, if this is an area that people are interested in and you want to know what's coming to healthcare, I would say look at some of these computer vision communities and conferences, because that's sort of the time lag that we've been seeing. And we're seeing that pretty consistently. So different techniques. So a lot of what has started in 2015, 2016, those are convolutional networks. And then we start to see recurrent neural networks starting to break in, different things around adversarial training that's now becoming very, very popular. And those are techniques that are now sort of are starting to mature in some of the other communities that are now making their way into healthcare. And there's been a huge explosion of startups in this space as well. So when I finished my PhD in 2012, there was only a few companies that were even working in the medical analytics space. So GE and Philips and Siemens, the guys that were actually manufacturing the hardware were pretty much the only ones trying to, outside of sort of general academic research groups, trying to do anything with that technology. And now we're seeing this huge explosion of companies trying to leverage this deep learning technology and apply it in the healthcare space. And so it's been exciting to sort of watch, but it's also, there's a lot still that needs to be figured out about how all of these different competing solutions are going to work out in a healthcare marketplace. And so some of the tasks that have proven very well suited for this type of work, things like early detection, screening, with some of the mandates around screening, especially with breast cancer screening, there's been a huge proliferation of data. It's about to start happening with lung cancer screening as well. There's many more studies than there are people available to read them, and the problem is much, much worse in developing countries than it is here in the US. And so this type of technology can be really, really powerful for helping to prioritize which studies get read first. We've worked with Ohio State University to develop a method for doing detecting critical findings in head CT. So that when a patient comes into the ER after a head injury, they're likely to go straight in and get a CT done. But once that CT has been performed, you need somebody to read it. And there may not be somebody on staff that's always available, or they may be overburdened with the amount of cases that they have to read and prioritize. And so what a system like this could do is to say, I believe with a high confidence that this patient has a critical finding. It's not going to necessarily say what that finding is. It just says there is something wrong with this particular patient. Read their study right away. That patient gets pushed right to the front of the line. Other patients that said, I'm pretty confident that these are normal patients. They're likely you're going to be able to send, discharge them right away, and they'll be okay without any side effects. And those patients can be read sort of secondary. They can just get a quick read from the clinician and move on. Quantification, I mentioned in the segmentation. That's an area that's really hard and time-consuming for clinicians to do, to the point that they actually just won't do it. One of the few ways that radiologists may do quantification, if they were looking at blood flow in a cardiac MRI study, for example, the way that they would do that now is they might just sort of click a couple of points. There would be some rough estimate. They click 2 points that would define a circle, and then they would do that at 2 time points, and it would calculate some ratio. And that gives a very rough estimate of how much blood the heart is pumping at any given point. With this type of deep learning segmentation technology, you can get very, very accurate measurements of that. And in a little while, I'm going to go through a demo that actually walks through how you would formulate a problem like that and actually come up with it for doing cardiac segmentation. Treatment planning then is related to that, so you can monitor the progression, identify what's going to be the best type of treatment for an individual patient. We're seeing deep learning come in at every stage in the imaging pipeline as well, so not just in the analytics stage. There's a group at Massachusetts General Hospital that was doing some work around actually using deep learning to do image reconstruction. So when these images are acquired, they're actually acquired in complex space. So they're not actually, what comes out of a scanner is not actually what's being acquired. So there's a lot of post-processing that goes on in order to reconstruct these images from this sort of raw input that's acquired by either a CT or an MRI or an ultrasound machine. What they've actually figured out is that you can teach a network to take that raw input and predict what the output is going to be with very, very high accuracy. And so you might think, well, why do we need to do that? We already have traditional reconstruction techniques. But what's powerful about this deep learning approach is that you can actually undersample your input space and achieve nearly the same output result. So what the network is learning to do is sort of interpolate some of the missing information and still generate a high quality output. This is has been a very active area of research. There's techniques, things like compressed sensing. And so this is sort of an alternative to that can still yield very high results. This would then allow you to reduce the amount of time that it takes to scan a patient. So if you're giving a CT, this could reduce the radiation dose. If you're giving an MR and somebody's claustrophobic, this now reduces the amount of time that they have to be in a scanner. So this is not just in terms of doing diagnosis and things like that. And I think that is what's been really exciting in the last year or two, is to start to see how this is going to impact just about every aspect of an image analytics workflow. And so, we've talked a lot about the analytics side, and then also on the rendering side, being able to generate high quality visualizations and things like that is also, people are also leveraging deep learning in order to do that. This technology is actually being brought right onto imaging hardware. So in partnerships with companies like Samsung and GE, this type of deep learning is now being applied directly on ultrasound machines. So now you can start to do some of these same analytics that a trained stenographer would do. It can be done right there on the machine. And there's a lot that could enable, so that if the system was able to detect, oh, you didn't acquire an appropriate angle for viewing this type of anatomy, then the stenographer would know that in real time and be able to adjust their protocol to make sure that they're acquiring all of the necessary information. There's a company called Arteris that they do blood flow quantification from cardiac MRI images. So this gives clinicians a measurement that they would never otherwise have had access to. And this is a great example because it's one of the first FDA cleared deep learning algorithms that's being applied today in the clinic. HeartFlow is another company that does something very similar, but from cardiac CT. So they're able to calculate a blood flow measurement called the fractional flow reserve. And that's something that normally would have to be done through an invasive catheterization procedure, but is now being able to be calculated directly from a CT, which is non-invasive. So, the benefits of this type of technology are really great. Outside of the imaging domain, genomics is a huge area where this technology is being applied. So obviously really high dimensional data, trying to identify patterns and correlations between genomics and phenotypes and things like that. High context screening, so for being able to identify the efficacy of different drugs and different biological models, pathology, and then looking at semi-structured and natural language text within medical records. So obviously there's a lot of information in the images, but there's also a lot of information in the reports, in the vital signs, in the lab measurements. And so starting to figure out ways to leverage that information is the area that companies like Cloud MedX are looking at. What are some of the challenges that have caused the healthcare community to sort of lag a little bit behind the state of the art in this technology? The first we kind of mentioned is data set size. So that ImageNet data set is 1.2 million images. I have personally worked on an image challenge for doing segmentation where there was 45 patients. And so, the scale is just so different between what is available in the healthcare space and what is available in the natural scene image space. But it is starting to get better. So there's a challenge out right now, the Dream Mammography Challenge, where they've released 85,000 patients. So now we're, orders of magnitude better than where we were, still an order of magnitude lower than what's available in other communities, but getting a lot better. The NIH just released a data set with chest x-rays with 33,000 patients with 100,000 images. And those are all annotated in both cases. So this is huge. It's starting to really get the field to where it needs to be. Another challenge is the diversity in the data. When you have a data set coming from, that a researcher has access to, they may typically, partner with a single clinical institution, or if they're at a university, they may have a single academic hospital that they work with and are able to get data from. The patient population is generally going to be, somewhat uniform across that particular institution. The acquisition of those images is also going to be relatively uniform. So, all of their hospital may use GE hardware, and so there are going to be characteristics of that image that may be only relevant for GE images. And if you're trying to then create something that's general and can be applied in other cases, you want to make sure that your network is seeing a diversity of inputs in order to learn what you actually care about. So that if what you care about is actually learning a representation of what the heart looks like, you learn what the heart looks like and not what a GE cardiac MRI scan looks like. And so being able to increase the diversity is really important for doing that. And also getting balanced data. That comes in sort of two ways. It's pretty easy to get uniform categories when you're dealing with types of cat. It's not that easy when you're trying to identify some rare disease that only a few hundred or a few thousand people actually have. Your population will be predominantly normal, and then a few examples of an abnormal case. And there are ways to get around that, but it's very challenging and something that definitely needs to be you need to be aware of as you're doing this type of training. And then also the balance within an image. So if you're trying to do object detection and the object is 70% of the image, like this cat, that's relatively straightforward to train. But if you're trying to spot a lung nodule in a three-dimensional CT scan, this may be, maybe 1% of your pixel data that you're trying to identify. How you approach that may be very different. Just to sort of illustrate some of the differences in the sizes that we're talking about. So CFAR-10 is sort of a classic image classification data set, 60,000 images. It was, it's kind of considered one of those deep learning 101 type data sets. You might start with that as something to work with. But the entire CFAR data set fits in one fraction of the pixels of a single digital pathology slide. And so, you know, the architectures that people are using for dealing with data sets of this size may not be applicable when you're now dealing with something that is, you know, 100,000 by 60,000 pixels instead of 32 by 32. And just to sort of illustrate that even further, that entire ImageNet data set is only 474 slides from a digital pathology lab. So the scale that we're dealing with in healthcare is very different. And so there are a lot of challenges that come along with that, not the least of which is the amount of memory that's available for doing this type of training, which is, you know, something that our hardware is may or may not be impeding on, depending on the applications that you're working with. Labeling data is really hard as well. If you're trying to do object detection and for self-driving cars, and you need to know where are the stop signs in this particular image, it's relatively easy to farm that out to thousands of people, get them to annotate these images. Actually just saw today for the first time, I got an image captcha, and it was identify which region of the image has a street sign. So, you know, they're distributing this task out to everyone and leveraging that type of data. If you want to then say, you know, where is the effusion in this chest X-ray? There's your set of possible labelers has gone down dramatically for that particular task. And so there has been work on associating the information within these reports that gets written about each of these images and tying that back to the underlying image so that you can leverage that for training. And that's actually what the group at NIH did to release this data set with 100,000 patients. There's no getting around that actually manually annotating data is going to improve the results, but it is a very time-consuming process. If you wanted to identify all of these different structures in this image, you have to think about the amount of time that it's going to take somebody to do that. And this is now multiplied by, in this particular case, probably 128 slices. This is not just a 2D image, this is a volumetric image of the entire abdomen. You're having to go through and manually delineate all of these structures. And so one good thing about this type of technology is that you can leverage the types of segmentation algorithms developed in other purposes and apply them here, and you're going to get a reasonably good estimate to start with. And so what that then means is that the manual annotator may just have to adjust a few points to improve the results. Then all of that can be fed back in, and this training can be rerun, and you can update these parameters, and now your network is going to get better over time. So that's one of the major powers of this type of technology. And an area that I'm really excited about right now is actually in simulating real data, simulating realistic looking data from artificial inputs. And so that's a very active area in the computer vision world right now. How do we you know, simulate images of people at very high resolutions? And they're actually doing a very good job at this right now. So you will see images that are synthetically generated of a person, and there's no way that you would realize that this was not actually a photograph of a real person. And so I'm hoping that we'll start to see some of that technology make its way into the healthcare domain, because we have an incredible wealth of knowledge about what's going on within the body. And so if we can create the types of models that are already prevalent in the community for you know, modeling electrical activity in the heart, we can then use that type of model, apply some of these image generation techniques, and now we could give it any set of type of diseases that we want, represent that over a huge diversity of image characteristics, and now train an algorithm over that, and hopefully it will get better over time. So we may not even need to actually image that many more patients. We could start to synthetically generate the disease distribution that we're interested in. And so I mentioned too, being able to leverage some of this technology that's available from other domains. And so you do that through a technique called transfer learning. And so what that is that at each level of these deep learning networks, the features have different representations. So in the early levels of the network, you might have low-level features that are going to be common across different imaging types, different domains. So these would be things like edges. So if you look at this, you can just see that these are sort of a series of oriented edges that this particular node in the network has learned is characteristic of these different classes of objects. As you progress through the network, the representation that the network learns becomes higher and higher level. So as you go through, you can start to see in the mid-level features, maybe you're starting to see representations that look like a tire, a bumper, a windshield. And then by the end, you can start to see things that look like cars. And so this collection of these early low-level features with some of these higher-level representations are what allows this network to learn to distinguish these different objects. But if you were to stop the propagation of an image through this particular network at a certain point, now instead of doing classification, you've actually just created an automatic feature detector. So that you pass an image in, get some vector of features out, and then you could use another classification approach to actually distinguish these different groups. And that has been the way that a lot of this technology has started to get into the healthcare space. If we look back at the papers that were in that original graph in that sort of 2015 timeframe, I would bet this is exactly the approach that most of them were taking. They were not training these networks end to end. They were not coming up with new architectures or anything like that. They were taking these pre-trained networks from other tasks, using those as feature generators, and then applying SPM or random forest or something like that to do the classification task at the end. And if you just Google that, you can find these things. So this was just somebody put up a GitHub project where they took one of these network architectures that won ImageNet in 2014, and then applied that same network architecture and those pre-trained weights as a feature detector, and then applied it to chest X-ray, and they get reasonably good results. And so what's really interesting about that is that it's a good way to start to see, is this problem that I'm interested in actually amenable to deep learning? Is there something there? If you start to see that this type of approach can give you reasonable results, then maybe it is worth investigating further and actually training the network from real data as opposed to leveraging this other type of information. So it can really speed up the progress in a particular application. And this is happening sort of across the board, this transfer of technology from different domains and making these networks many more general. So to show how this is sort of changing the research workflow, so that data set that I mentioned from NIH was released on September 27th. So this is 30,000 patients, 100,000 users. If we were taking sort of the traditional computer vision approach, this would take us a really long time to start to even digest what is actually in. So if we were trying to distinguish, I think there's 16 different diseases in that. The amount of time we would spend with clinicians trying to understand, what are you guys looking at to distinguish these different classes? Okay, so take that information back. Now we have to digest that and come up with a set of features that we're going to hand design and hand code to actually extract out information that may be relevant for distinguishing these different diseases. Then we have to apply that. We're going to test. We're going to iterate through that. From the time that a data set like that would come out to getting something with reasonable results, you can easily see how that would be at least a multi-year process. On November 14th, a group at Stanford from a very well-recognized professor put out a paper that they were achieving near radiologist level accuracy on distinguishing these different classes from that data set. So in about a month and a half, they took this entire data set and were achieving near radiologist level classification. And so this is totally changing the way that everything is being done in this field. That type of speed and that type of progress is just unprecedented in previous workflows. And now, there's a lot of caveats with that, and then we get the PR headlines that go along with whatever comes out in these papers, especially when it's coming from well-respected groups. But there is some things to be aware of, and so what's happening is clinical data is being taken and digested by data science groups and deep learning groups without necessarily understanding how this is being developed or applied in the clinical domain. And so one of the major sort of pieces of criticism of this work is that a radiologist typically would not actually diagnose pneumonia from a chest X-ray. So these patients have that disease annotated in their record because it's known that they had that. But where that diagnosis came from is likely a combination of the findings that this radiologist saw in the X-rays. There's something that may be characteristic of pneumonia, but it could also be characteristic of, I think, something like 4 other diseases. So some of the imaging characteristics there are going to be very similar. And it's only sort of in combination with these different features that they're able to make a final diagnosis. And so then to say that, you know, this network is as accurate as a radiologist at this task, well, radiologists don't actually do that task. So as we start to, you know, evaluate these different metrics and, you know, say how, evaluate the performance of these different tools, it's important to sort of keep some of these things in mind. Is the task that's actually being done, is this a real clinical task? Another really popular one is actually predicting the onset of disease. And so, you know, that's one where you can do that from medical records and things like that. Doctors don't do prediction. They do diagnosis based on the current state of the patient. And so to say that the network beats a doctor at predicting the onset of disease, well, yeah, I should hope so. Doctors don't do that on a day-to-day basis. These networks are very good at doing prediction. That's exactly what they're designed to do. So making claims that, you know, these things are better than or anything like that is a bit of a stretch in a lot of cases. But what this really is are new tools that these doctors are going to be able to leverage to drastically improve their workflows. And I had a few other examples. I'll just do these really quick of places this is coming in technology because I want to get into a demo before I run out of time. So one really cool area that's happening right now is around what's called radiomics. So this is actually associating genomic information with imaging information. There's a group at Mayo Clinic that is taking genetic information, using deep learning, and training the network on a specific genotype and an associated image. And the network is actually learning to associate the underlying imaging characteristics with the particular genotype. And so this is really powerful because now you can start to optimize your treatment based on a genetic profile without actually having to do that same genetic test. We talked a lot about the quantification. Zebra is an Israeli company that's starting to do some of that. They've actually just launched a service where you can upload an image and get a read for the whatever handful of diseases that they can detect for $1. So you can actually try it out through their web portal. Mount Sinai Hospital has been developing some of the EHR type technology for predicting disease. I mentioned Cloudmedics. Case Western University trying to do sort of similar to the radiomics idea, associate the underlying genomics information with the pathology slides. And PathAI, a company trying to then take that incredibly large image space that we talked about, so these 100,000 by 60,000 pixels, and help drive the pathologist to certain regions that are likely to be abnormalities so they can improve their workflow. And all of these different solutions, you can see how this starts to get a little bit muddled. If you have one type of image, you have to go to this service. If you want one disease, you have to go to a different service. And so there's definitely a push within the community right now to develop sort of a marketplace for these type of applications. We at the RSNA conference 2 weeks ago in Chicago, this is the Radiology Society of North America, Radiologic Society of North America. It's a conference with about 55,000 attendees every year in Chicago. Announced a partnership with Nuance to help bring some of this technology to life, so that now people can publish these models in a common model store, essentially, and then clinicians can access it through the regular clinical tools that they're already using. And then what's really powerful about that is that the more people you get this technology in front of, the more feedback your model can get, and the better that model is going to get. And so I know I covered a lot of information, but I want to give sort of a quick tutorial of if this is of interest to anybody here. We have created a tool called NVIDIA Digit. So what this is a web UI to actually start doing deep learning training. And you can do that without having to write any code. So it really helps to understand the type of workflow that people can use if they want to apply deep learning in their particular instance without necessarily having to be an expert in Python or TensorFlow or Caffe or any of those things. And so the particular example I'm going to show is around cardiac MRI segmentation. And so this is what the data set looks like. So you have slices of cardiac MRI on the left. And so this is the heart here. So we have the left ventricle, the right ventricle. And what we're interested in doing is segmenting out the blood pool. So that's really important for evaluating cardiac health. So how well the blood is pumping, how well the heart is pumping. And so that's why this is something that would be of interest in the clinical domain. And we can do that all through this web UI. Let me pull this up. So when you log into, and sorry, let me go back. And I'll put the URL up, but Digits is freely available. You can download it online from our developer website. It will run on any computer that has an NVIDIA GPU. And if you don't have that locally, all of the cloud service providers now offer GPU instances. So it's really easy to get started with this type of technology. And so when you are trying to train deep learning, we sort of talked about what the things that you need. You need the data set, you need the model, and then you need to actually do the training. And so when you are defining a data set, if you want to use Digits, it's as simple as identifying the specific task that you're trying to do. So if you want to do classification, object detection, segmentation, in this particular case, we've created a plugin so that it can handle the input type for this particular data. So those images that we saw previously, those masks were created from text files. And so that's just because that's the way that this data was distributed for this particular segmentation challenge. So you can define the task, and then it's simply a matter of pointing this at the location of your particular data. And then saying where your annotations are. And then this will read in your data set. And the reason that you need to do this is it's putting the data into a single database format that these different deep learning frameworks can interact with. When you're trying to process large amounts of data, if you were trying to read every single one of these files every single time that you're accessing it, that would be a big inhibitor to training this in any kind of efficient way. So all this is doing is creating an efficient representation of that data that these deep learning frameworks can leverage. And so once you do that, you can see all of the different data sets that you would have available. And all of this, even though this is running through a web UI, is actually being run locally on your computer. So none of the data ever leaves your machine if you're working on an application where privacy is of a concern, which is often the case in the healthcare domain. And so then after that, you want to define what type of task you're going to perform. So in this particular case, we're doing segmentation. So again, we want to do a segmentation task. And so we can simply select the individual image set that we're working with, and then define some of the basic parameters that you would want to use when you're doing a deep learning job. So an epoch is just how many times you're going to pass over your entire data set. When you do this deep learning training, you split up your data set into what are called batches. And then each time you update these weights in the network, you've trained with one particular batch, and then you do that over and over again until you've completed the entire data set, and then you start again. So it's a very iterative process to train these networks. And so these parameters are just related to how long you would want to do that, how you want to batch your network, and things like that. But typically, when you're doing this, you wouldn't want to just start this job from scratch. You're going to be able to find network architectures that have proven to be very successful for this particular task. And so we have ways to do that as well. So in pre-trained models, we've actually started to try to populate some of these common model architectures. So I think I mentioned that guy did the chest X-ray classification using VGG. So that network is there. The weights are all pre-trained. AlexNet was one of the first ImageNet winners. That architecture with pre-trained weights is available. So you can simply download these as a starting point to get going with your particular challenges. And then I won't go through all of the different iterations, but if we just take some of these things off the shelf and apply them, then when you do the training, you get these performance graphs. And so what you'd be looking at is how accurate your model is doing, how the training is progressing. You define what's called a loss function. And there are standard loss functions that have proven very successful for different tasks. So none of these are things that you have to sort of create from scratch. You can leverage the other information that people have done. But if you do want to create things from scratch, you can do that as well. So what this particular job has used a a specific Python layer that somebody has designed. So in segmentation, especially in the medical domain, there's a metric called the DICE metric that is typically used for evaluating segmentation accuracy. It's just basically a measure of how well two things overlap. And that proves very successful for the medical domain, where some of these objects may be very small, and so you need to have metrics that are independent of the area of the object that you're trying to segment. And so you can apply those. And then when you actually run the training, you'll get plots like this showing how accurate your model is. And you do that on both a training set, and then you have a separate set that you keep for validation, and so that you don't overfit your network. These networks can get so complicated that they can, it's mathematically shown that you can develop a network that, given a complex enough architecture, you can map any input to any output. That's not necessarily what you want, because that is just then memorizing your input data. You don't want that, because then if you give it a new case, it's not going to know what to do with it, because it's only memorized the training data. So there's a lot of work in this field to help make these models more robust to this type of training and accuracy. That's why you would then care about how this model is performing on your validation set, so the images it hasn't actually seen before. But then if you were wanting to start this, use this as your baseline, it's really straightforward. So you can simply clone this model. This takes that previous iteration and says, I'm going to start from there. And so now we can train it for another high number, so that we can look at a few of the other things that it allows while it's training. You can set some of these other parameters. We have this custom layer for calculating our DICE coefficient. And then if you want to actually customize any of this, you can get in at the code level. You can see these different layers. It's written in a very high level way, so it's really easy to see what these things are doing as you start to learn about the different types of network layers and network architectures. These are very common things, so doing convolutions and pooling and things like that. Those would be very common layers in a deep learning architecture. And so you can go in and modify some of those parameters if you want. You can see a visual representation of what this graph looks like. So that if you read a research paper around any of these topics, you'll typically see something that looks like this. And then you can go ahead and kick off your training. And so this is running on one of our servers, so we can leverage a great amount of compute power. And then we can name that. And so now this will kick off our training job, and we're able to monitor the progress. So we can see those performance metrics. We can see information about the compute resources that it's using. So all of this is being run in Santa Clara at our headquarters. So there is some time just with passing data back and forth and things like that. But once the job gets going, all the data will have been cached, and then we'll start to see this. And when you go back to the overview here, we can start to monitor the progress of this job. And so this is really important. If you have shared resources or things like that, you could use this to schedule jobs among different users. And when you're monitoring the performance, once it gets going, you could then see, okay, this model is or is not converging. So I could stop if it seems like it's not progressing in the way that I want. No need to let this run for 2 hours if I'm never going to reach a reasonable solution. I could see, oh, it's already plateaued. I've reached the maximum accuracy for this particular model. And then you could move from there. And so then if you want, once you have your model that you're happy with, and you want to actually apply this to a new unseen case, there's inference capabilities too. And so you can just come down here and say what we're trying to do. We're going to stick with our LV segmentation. We're going to do image segmentation. We'll just give it plotting color, and then we can apply one of the images to see how well this network does. And then again, this takes a second because it's passing the information back and forth, but the inference process itself is actually really, really fast. You can do this in fractions of a second, but then this is passing back a lot of information so that you can actually dive in and see like what the network is actually doing on this particular inference case. And so I would really recommend this as a great way to start to get started with deep learning if it's of interest. It's really straightforward. And one of the most important things is to just understand what a deep learning workflow looks like and how you might start to have to think about organizing data, managing data, and then what types of decisions you would have to make going forward as to the types of tasks that that deep learning can be applied for. And I guess public Wi-Fi network over VPN and things is a challenge. There we go. So now we can see this is the output from this particular network. It looks very good. We could see from those performance metrics that we were getting a dice coefficient in the sort of 0.86 range. Typically in this field, anything over 0.8 is considered good. And this is a relatively small data set. This is using a network that was trained on image classification for general scene images and just applying in this particular case. And so this really starts to show just how powerful this technology can be. And what we're starting to see now is people are developing these architectures and things specifically for medical imaging data, and the results are really, really outstanding. And so I just want to finish up with one more pointer to where you can get more information about this type of thing. So a lot of what we do is around education. So we have what's called our Deep Learning Institute, and this typically takes the form of hands-on workshops that we administer at conferences or at other events or different and things like that, where we can tailor a specific deep learning curriculum to the interest of the users, and then they can walk through actually doing the demo that I just showed. So we have a particular lab where you actually do it yourself. So on an Amazon Web instance, you launch your own instance of digits and walk through that entire training process and get an opportunity to play with the different parameters and see how that affects your results and things like that. And these are also available online. So if you go to nvidia.com/DLI, it has links to the online courses as well. I think there's about 4 or 5 that are freely available. One of the best ones to start with is called image classification with digits. That just looks at classifying handwritten digits. But then if you want to do the actual the demo that we just did, that's called medical image segmentation with digits. So those are all available for people to play with and hands-on experience. And so, we talked a lot about all this hype and things like that with AI, and I just want to sort of end with this quote because I think this is really exactly where the field is headed. So artificial intelligence is not going to replace radiologists, but radiologists using artificial intelligence are going to replace radiologists without it. And I think that can be, broadened out to pretty much any aspect of healthcare. And to be honest, most aspects of any professional job at this point, this technology is going to touch just about everything that we do in our daily lives. And so being aware of it and sort of ready for it and on the cutting edge of it is really going to be a major benefit to everyone. So thank you all for your attention. Is there any questions?
Is it intended to be a playground for learning, or is it intended to be like a replacement for?
Yeah, so what you'll likely find if you start playing with digits is it is a great way to get started. Not every feature is supported within it. If you start getting into really fancy architectures or custom networks, there may be features that aren't supported. For example, if you wanted to do volumetric imaging, so dealing with 3D images, that's not supported right out of the box. So you would have to figure out how you want to do that. The way that people typically do that is you take a 3D image and you make 2D slices and then you load it in. But if you actually wanted to do 3D convolutions and things like that, you would run into some challenges here, and you'd be better off sort of just moving into TensorFlow. Right now, most people are using Keras and things like that. So those would be sort of the way to go. It's a great way to understand the overall workflow and how to get started, but we typically see that people will sort of move off it.
How does regulation play into like healthcare adoption?
Yeah, so it's a really good question, and to be honest, it's something that the FDA has only just released some initial guidelines around. But it's from one standpoint, it's positive that they're recognizing that some of their regulatory protocols are not necessarily designed to deal with this type of situation where these systems can be constantly learning and adapting and things like that. They don't have policies in place to deal with that. But if we look at sort of traditional software development, things like that, we can take a lot of information from that. So, the way that this will typically be done is you would have sort of a release schedule. So even though theoretically the network could be improving on the fly, that's not actually what you're going to see in practice. So you would deploy sort of, version 1.0 of your model. It would be out in the field for a long time. You would be getting some kind of, feedback from the users, taking that, updating your model. You may go back and even make some architectural changes based on what you found and things like that, and then you'll release version 2.0. And so that's why a lot of companies have gone to like cloud strategy. So companies like Arteris and HeartFlow, the way that their systems work is that you actually upload your images to their server, it does its analytics and gives you back a report in a format that whatever PAC system or DICOM viewer or things like that you're using, that you can then ingest that output and it gets into the healthcare. But yeah, so companies are navigating it. It is something that you can get through, but yeah, it does.
Are there any open source platforms just like ImageNet where patients can voluntarily post their own radiological images and give their diagnosis? They can leave the PI out of it. Are there any?
That's a good question. Not that I know of. No, I haven't heard of any kind of platform for sharing things like that. To be honest, if I had to guess, it wouldn't get to the scale it needs to be in any sort of efficient manner. The number of patients that actually even collect their own scans is, I would say, relatively small at this point. And then the percentage of those patients that would be willing to then upload their images to some public server, also probably relatively small. I think that, a more realistic way that this data is going to start to be distributed is through organizations like the NIH that are creating, large-scale collections that can. With the shift to cloud storage and things like that, a lot of hospitals, and especially hospital networks, are now starting to have access to much larger image sets. And so, obviously that's been private and proprietary to them, but these collections are being created.
Also, a lot of larger hospitals are moving to similar HIS systems, which maybe do backdoor entry into those images.
Mm-hmm.
And that will give you a data set. Yeah. Stanford and Vanderbilt not use the same HIS system.
Yeah, exactly. And I think that is where a lot of this is going to come from. It's from sort of like research institutions like that are trying to put that out there. This guy actually, Kurt Langlots, is a professor at Stanford, and he's talked about trying to create the ImageNet for healthcare. And I think that it's largely going to come from like the researcher, PI-driven approach, as opposed to sort of general people in the public uploading their own images. Yeah, create some kind of incentive or enjoyment factor. Yeah, definitely.
So I have a question about, so all these algorithms are trying to mimic or excel human performance. So on the human side, say radiologists, they're not born radiologists. They go through a couple of years of training to become experts. And then on the algorithm side, they also need to have the original format and then went through a certain amount of training, and then eventually the algorithm has matured. Is there any work that compares these two, the training process for human and for the algorithm, and to see if there's anything to be learned from it?
Yeah, so being able to start to take some of this technology into the digital domain is a very active area right now. And one of the challenges is actually understanding why a network does what it does. So, people often refer to this as sort of like a black box technology. And so one of the active areas in research on the sort of deep learning side of things is how do we tease out what's actually going on inside of that black box. And so what we find is some really interesting things that actually could then guide sort of the training or treatment process. So one of the ways that some of these companies start to output their results is through like a heat map. So for example, with this PathAI, so what they, this actually probably isn't the best image to illustrate it, but they've highlighted regions where it thinks there's a problem. And so this same type of output can be generated from some of those classification numbers. So if you were trying to distinguish tuberculosis, and you know that that's going to be affected, a certain portion of the lungs is going to be affected, if you then look back at what areas of the image the network is paying attention to, you'll actually see those regions highlighted. And so that does two things. One, it starts to give you a sense that this network actually has some understanding of the thing that I care about as a clinician. But it also could then start to lead you to look at things that maybe you didn't necessarily associate with this particular thing. So you can sort of feed that back into the training process and then maybe, derive some new insights about that.
Some of the big tech companies are pretty directly involved in this space now. IBM and Microsoft Health, and working with hospitals and academic institutions. Is a company like NVIDIA getting into this space, or go more on the hardware?
Yeah, so all of those companies are using our hardware. So we sort of just, the way that we interact with them is to make sure that their needs are being met by the hardware and solutions that we've heard about. We are starting to investigate, is the healthcare space an area where we need to put individual focus to help develop technologies that are sort of off-the-shelf products are not needed. We did a similar thing in the self-driving car domain. So we realized that people were using these for developing self-driving cars, but the systems that they then had to install in the car were massive. We have a great visual of one of the companies, their entire trunk was computer hardware in order to navigate the self-driving car. And so through sort of focused effort in that particular domain, NVIDIA took what was an entire chunk and brought it down to a board that's this big and about that big. And so all of that same technology is now encompassed in this single hardware. And then what that also leverages is this integrated software stack on top of that, which is what allows for a lot of this progress to be made. So that's sort of the way that we typically work with healthcare customers. So we will help to guide what solution is going to be best for the particular problem that they have. All of the cloud service providers offer this hardware direct to consumers, so that's one way that people can start to interact with a lot of medical imaging researchers and things like that work with the hardware. But yeah, so we're likely will never be launching any kind of direct to provider solution, but it will be through all of these other industrial partners.
Who faces the legal battle of this if the wrong diagnosis is made?
Yeah, so that's still up in the air at this point. Depending on who you talk to, the companies are going to say that the doctors always have final say, and likely all of the terms of use of all of these devices, that is going to be what is written explicitly. So, I mean, that's some of this technology has been around. There's CAD systems and things like that, and the way that those systems are put into practice is that the clinician always has the final say and the final read, and so it's going to be their name. And what that also does, though, is it puts the onus back on the algorithm developers to make sure that their algorithm is actually doing what it says. Because the first time a clinician gets hit with a lawsuit because that technology missed some finding that this doctor is now being sued for, or your reputation is over. That software is never going to make it back in the market. And so, even though they may not have the legal burden, they're going to have sort of the burden of proof heavily put onto their development.
Thank you all for your participation. engaging and highly informative. And also, just a note that we'll change our meeting time to third Tuesday, starting next month. So we'll post that information on the meetup page.